Hi, this is Gordon Parker from Michigan Tech, and in this video we'll make a model for an en masse vibrating system. If you've made it this far in the series, you're indeed brave, and I must say that I admire your tenacity, but I think this topic is going to be the payoff. As a recap, Video 1 was an introduction to SimMechanics with one vibrating mass. Video 2 was honestly a bit boring, but I think it was necessary to show how easy it was to change the orientation of the spring and mass system to, say, an inclined plane or hanging from the ceiling. Video 3 was great fun, exploring how to manipulate the model using the set_param command. But in all of these videos, we were focused on a rather simple single mass system, and thus we weren't exercising what I would argue is a significant feature of component-based modeling code such as SimMechanics. In short, we can change in seconds the complexity of a model and explore the effects of the change. In our case, this means going from one mass and spring to having 2, 3, or 4 or more. Now, deriving the differential equations is still important, but for systems with many masses and springs, this can be time-consuming, and frankly, the raw differential equations don't give a spectacular feel for the resulting motion of the system of bodies when, let's say, you give it a push. So here's what we're going to do. Instead of building on the previous models, I'm going to start from a blank slate and build up the single mass example, and then show you how to add an external force to the mass. That's something that we haven't done before. And with all the skill we've developed in the earlier videos, this whole process is just going to take a couple minutes. Then we'll simply replicate a subset of the model as many times as needed to make our multi-mass system. But first, I'm going to sketch by hand our many spring and mass system to illustrate the equation development process. I'm a huge believer in using multiple strategies to analyze a single dynamic system. I would never want to leave you thinking that using SimMechanics by its lonesome is a proper analysis approach. Using multiple analysis schemes gives you an opportunity to check, let's just say, competing results and tease out any mistakes. So with that, let's get started with the hand calculations. Okay, let's start with just the single mass system first as a bit of review. So here's a fixed support. Here's our mass. We'll call it M1. And we'll attach it with a damper and a spring. And let's apply an external force. We'll call that F1. Let's put these labels on here. And let's see, it's always good to have a coordinate frame. And we're going to have, let's call Z the direction that the mass travels in. Now we'll make a free body diagram, so we'll just extract that mass from the connections with the spring and the damper, and then apply all the external forces to it. And let's define the variable of motion of that mass. We'll call it Z1 from the equilibrium configuration or the unstretched spring configuration. And we'll put on an inertial force, M1 Z1 double dot, the damper force C1 Z1 dot, and the spring force K1 Z1. Here's our F1, and just for completeness we can put in the M1G and a normal force, even though they don't really enter into this analysis. Okay, so now we can write down the equations of motion, just sum up all those forces. So we have an inertial force, the C1 Z1 dot, plus the spring force K1 Z1 equals F1. Nothing too exciting there. But now let's go to the many mass system. And in general, n masses, so we're going to need a lot more room to do that. And here's M1. Again, there's our damper and a spring. Force. We'll apply forces to all the masses. What the heck? And there's another spring, another damper, another force. Dot 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 is just saying that we have a whole bunch of masses connected. And then we get to the n-1 mass. So we're almost at the end of our chain. And here's the nth mass. And again, we connect them with some springs and dampers. Apply some external forces. And put on our labels. Now we can do the same analysis approach we did before, start making free body diagrams. And let's just do it for 1 and 2, just to kind of illustrate the procedure. And we get the same inertial force, damper force, spring force, our external force, F1, and the normal force and the gravity force. And now we have the spring and damper force that interconnects M1 and M2. So our damper force is, C2 times the difference in speeds between Z2 dot and Z1 dot. And similar with the spring force. So I think we've got these labeled up now. And at this point we could write equations of motion, but that's an awful lot of writing and time consuming and potential for mistakes. So instead we're going to skip that process and go straight into SimMechanics to develop the model. So here we are in MATLAB, and we'll just use our smnew command to bring up a template SimMechanics file. Let's see, we have this Explorer that I don't like to use the graphical version, so I'll just get rid of that. And let's save it off as nmass, since we are going to be working with n masses, actually 3. Let's just work on some of these blocks left to right. So let's see, this is the one that defines our gravity vector. And let's just go ahead and fiddle around with these block annotation properties so that we can see what direction the gravity vector is in. So grab a couple tokens, rearrange them, and we'll just denote this as G. There we go. And once we say OK, now we can see on the front face that gravity is in the Z direction with this funny value. And that's as good a value as any, so we'll just leave it alone. So remember, the world frame has the y-axis by default into the page, and so we're going to rotate that by 90 degrees about the plus y-axis so that the z direction is, left to right as we would be looking at it here. So there's plus y, 90 degrees. Now we have a nice rotation matrix, but it's always good to be able to see that on the front face of the model, especially with these pesky rotation matrices. Otherwise, you have to keep clicking into them to see what you have. So we'll just grab a couple tokens that describe the angle and the units and the standard axis that we're using. And put in our own custom annotation. Boom. So now we can see it right there on the front face. So that'll rotate our world frame by 90 degrees. And let's take this thing and just create a subsystem from it. Just by clicking on that auto prompt, and we can call this the world frame. Very good. Go back to the high level, and we can just call this config. There we go. Just cleans up the block diagram a little bit. Okay. Now let's grab a joint, a prismatic joint to be precise, because we're going to be using some linear springs here, spring and dampers, just like we did in videos 1, 2, and 3, I believe. So there we go. We'll just call it spring 1. And then there's a whole bunch of properties in here that we're going to set, and of course make them visible on the front face of the model using the block annotation. So let's go in here. And the first thing we're going to set is the location, the initial location of the follower frame relative to the base frame. And that's this quantity, and we'll give it 10 centimeters just like we did in the previous videos. Then we can set our spring information. So this one is the relaxed position of the spring, or the unstretched length of the spring. We'll set that to 10 centimeters also. And then the stiffness and damping. Give it a lot of damping this time. Now here we are in actuation. Remember, we're going to add external forces, but this is not the place to add an external force. Because if we could put a force here, but really it's being applied equally to the follower and the base frame. So it's really not an external force, it's really an internal force. And there we have a position sensor. So now we can see another port that's been added. And let's fix up all these properties. There's a bunch of tokens we need to pick here. The equilibrium information, that's the starting distance of the follower from the base. Always good to think in terms of followers and bases for these joints and frames. The spring stiffness, and finally the damping coefficient. There we go. And now we can just reorganize these a little bit so that we have 4 separate lines of information, and then we'll give them some somewhat descriptive names. So we call this one, let's see, Z. There we go. K and a C for the damping. Perfect. Okay, so now we have our spring all set up, and now it's time to work on the mass 1. So let's call it that. And let's flip it around. You can use Control R on a PC or Apple R if you want to flip that block around. And we'll give it the same size that we did in the other videos, 1, 2, 3, pretty creative, in centimeters, and make it a mass instead of calculated from a density, and set it to 0.15 kilograms. And let's make it yellow. And there's a method to that madness. Since it's the first mass in the chain, and the plots that we'll be looking at in Simulink go yellow, blue, red in terms of the line styles, we might as well start the first mass as yellow so that it is color coordinated with the Simulink plot window. Great. And so now we can hook this to the follower frame of the prismatic joint. Get this out of the way. And I've scooted the block around a little bit so that it lines up nicely. And there we go. So now let's apply that external force. So I'm just going to grab a external force torque block, and let's explore this a little bit. Notice that, as the name implies, we can apply forces or torques in any of the axes. And we're just going to apply force, and we need to put it in the Z direction because that's the direction that the mass is sliding in. If we put it in another direction, it really wouldn't do much because the mass is constrained to only move in the Z direction. Now you can see that the block diagram is a little bit larger than the screen now, and so you'll notice occasionally that I'll hit the space bar, and I won't always say that, but you'll see it instantaneously fill up the entire screen. So just keep an eye out for that. Okay, so now let's get our input into this thing, and we can put any kind of input into it we want, but let's do a pulse. And so I'm going to make that pulse using 2 steps. So this step starts at 1, it has amplitude of 1, and I'm going to add it to this step, which I'll set the final time to be 5 seconds, and the amplitude -1. So when you add those two together, you get a pulse of duration 4 seconds. So I just need to add those up. And maybe I'll stretch this out a little bit. So that things line up nicely. There we go. And I need a little bit more room because what I also would like to do is to be able to turn this pulse on and off easily. So what I'm going to do is stick a gain in. Oh, hold it, I can't connect this. And the reason should be pretty clear. That signal coming out of the adder is a Simulink signal, and I need to change that to a physical signal that's consistent with SimScape. So I just use the Simulink or the S to PS block, and we're good to go. So now I'm going to go and grab this gain, which will let me do a switch in kind of a crude way. I can either set this to 0 to turn the pulse off, or 1 to turn it on, or anything other than that if I wanted to gain up the amplitude of the pulse. Now I'm going to take this and turn it into a subsystem. Again, just to kind of clean up the block diagram a little bit. And I'll label that pulse, just in case I forget. Label the output pulse. I just left-clicked into that subsystem. And I could call that switch or on-off or who knows what, but that's good enough. A little bit of description. Now, we want to look at that position sensor. So let's do this a little bit differently. This is some new stuff. I'm going to use a from and a go-to block, or go to and from. Scrunch these down a little bit, and these just let us move signals around within the block diagram without requiring me to actually connect things physically with lines. So I can just, and here I go again. So the output of that block, that prismatic joint, is a physical signal, and I need to change that into a Simulink signal. So let me grab this converter, stick it in here, and now it's good to go. And the output of that signal I've labeled as Z1, and using the from block, I can set that to Z1, and then that signal just goes right from the output of right from that go-to block to the from. And I can have as many of those froms as I want, so it really lets you clean up the diagram quite a bit. And here's our converter from meters, because that sensor is in meters, and I need to convert that to centimeters. And let's just update the diagram. That'll bring up the Explorer. Turn on the frames. Go to the pan tool and scrunch it down a little bit so I can see everything. There I can see the world frame on the left and the prismatic joint frame that's also attached to the yellow mass. Okay, let's just run this. So the pulse goes on, then it comes off. Beautiful. Oh, but there's nothing here. And the reason is I did not go ahead and adjust that from block. See, the go-to says Z1, but I never changed the default value of the go-to block. So I just update the tags. I grab the Z1. Okay. Save it. Save early and often. And let me move this over a little bit so I can see it populate at the same time that the model runs. And boom. Ah, there it is. Pulse on. Pulse off. Looks good, but it's all choppy, and we've seen that before. It's using a variable step solver, and so what we're going to do is just constrain the minimum time step for the solver to something that makes it more pleasing to the eye. So I'll use 1/60. Now everything should be very smooth. Very nice. And the animation even looks better. Okay, so this is really just taking us back to starting from scratch and making up a one mass system. It took a few minutes, but it's worthwhile to do that every once in a while. But here's the cool part, is now we can extend this out to multiple masses, multiple vibrating masses in just a couple seconds. And all I'm going to do is configure the part that I want to replicate, which is all this, do a nice little package. Left click drag to copy it, or to select it, and then right click drag to copy it. And then just connect the second prismatic joint to the output of the first, and I'm done. I now have two masses. I can replicate this process again to make three masses. I could keep going as many times as the day is long and make a huge chain of vibrating masses, but we'll just stick with three. So now let's take a look at this in the Explorer. I have to update the diagram. Oh, I got a little error. And the error is saying that I have multiple go-to tags with the same, or multiple go-to blocks with the same tag. And that's because I didn't change these. They're still set to Z1. That's actually a good error to be aware of, so that there's no conflict between a go-to and froms. So there we go. Now we have Z1, Z2, Z3. Let me change these colors. The second block I'll make blue so that it's consistent with what I know is coming with the Simulink plot window, which goes yellow, blue, red by default. So then I'll make the third mass red. Oh yeah, there we go. Now if we look in here, it should be much prettier. Ah, beautiful. Scrunch it down, scoot it over, and we're ready to play. So we run it. And there it is. Now remember, we have pulses going into all three masses. So it's a pretty profound external input to the system. 3 pulse forces, 1 applied to each mass, all occurring at the same time. But we can easily turn those on and off with those little gain blocks that we added. So we'll play around with that. But first, let's get everything, all of these nice position outputs into a single scope. We could have multiple scopes, but then you'd be clicking around to see who's who. So we'll grab a mux block. There it is. Increase its dimension to 3. And then replicate a couple more go-to blocks, or I'm sorry, from blocks, with the Z2 and the Z3 signals. There we go. Now I can squeeze in my mux block. That takes 3 scalar signals and turns them into a pipe that has 3 signals in it. And we'll just select and then right-click drag to copy it. There we go. Now I have all 3. And I just need to make sure that the tags that I've chosen are Z1, Z2, and Z3. Update the tags and pick a Z2. Update the tags and pick a Z3. And let's turn this one off. There we go. So we've turned those 2 off. The only pulse being applied is on the 3rd mass, on the red mass, when we go into the Explorer, that one on the end. Let it rip. Boom. And there's the pulse on. And there's the pulse off. And we can certainly look at it in the Simulink plot window also. I'll just hit the space bar so that we see everything in the window nicely. But let's go in here. What we'll do first is let's get this thing rattling around a bit. So I'm just going to get rid of the damping on all 3 spring mass damper systems. I'm just setting the damping coefficient to 0 in all of these. That'll make for a little bit more interesting response. Update and then run. And now you can see things wiggling around relative to each other. It's important to note that the position sensors that we have are all measuring distances between the base and follower frames of those prismatic joints. So they're all relative distances. Let's gain this down just a little bit, just so it isn't quite as large of an amplitude. And there it goes. Now there's our plot, and you can see that at time equals 0, everything is at 10 centimeters, because again, those are distances between the base and the followers of all those prismatic joints. And then they move from that. And you can see there's some, interesting response there. So there you have it. So this is a powerful aspect of component-based modeling. It's being able to rapidly extend a simple model to a rather complex one with just a few clicks or drags. And once in place, we can explore different scenarios and start becoming acquainted with how the system behaves under different parameters or initial conditions or forcing functions. Now I've kept this example vibrating on a horizontal surface, but if you use the methods from videos 2 and I think 3, you can quickly change it to a set of hanging masses or vibrating on an inclined plane, etc. But I'll leave that to you to explore and to create some schemes to find the system's static equilibrium. It's a little bit more tricky with multiple masses. So have fun with it, and again, this is Gordon Parker from Michigan Tech, and thanks for watching.